Cool. Okay. So this is going to be note 9 on error correcting codes for CS70. First off, we're just going to kind of describe what the idea behind error correcting codes is and what it aims to, solve. So imagine that we're sending something over an unsecured channel, and there's the possibility that some of these packages get dropped or lost or corrupted. A high-level solution is to introduce redundancy to basically pad against missing content, and the method we're going to use is called error correcting code. And so this is a branch of information theory, and it's going to, some of the uses are when we transmit data over cell phones, satellites, TV, things that use radio. Okay, so let's actually look at an example of how we're going to use this. So imagine that we're sending n packets, n equals 4 in this example, but k of them get lost, where k equals 2. So how would we get around this? Well, as we mentioned, we are going to want to introduce redundancy. So instead of just sending these 4 packets, if we know that 2 of them are going to get lost, then we're going to send 6 packets. So that even if 2 of them get lost, we can reconstruct the original message given the 6 points. Okay, so I'm actually just going to display the image just to kind of formalize what I said. So again, 4 packets are sent originally, but we're going to encode our message by sending 2 more packets, where 2 is the number of packets that we know will get lost. And so once the person on the receiving end gets that message, the encoded message, there's going to be 2 missing components, but given that from our original message, we'll find this out, but you can construct a polynomial of degree n-1 or of degree 3, then you can reconstruct any missing points that you would want. Okay, so let's actually look at this. So the setup, use arithmetic and polynomials. We're going to be in the mod space of Q, where Q is a large prime, and we're just going to be we're going to let the set of messages m1 through mn be this thing right here, essentially. Okay, yeah. Okay. So step 1, we're going to create our polynomial that's going to be degree n-1. And remember from before, we're going to want to make sure that our polynomial goes through every point listed in our message set. So we will look at an example down there, but that's, yeah. So, yeah, this is going to be the original message sent. The code word is going to contain 2 additional points. And yeah. So notice we're going to keep our polynomial's degree the same. It's going to be degree 3, which means it really only needs 4 points. But we're going to generate 2 more points that will go through that polynomial, so that when we get to the receiving end, even though we only have 4 points, we will still be able to construct the polynomial because it's a degree 3. Hopefully this makes sense. I've kind of been saying the same thing in slightly different ways. Another thing to note is that n plus k must be less than or equal to q. Remember, our mod space is that large prime q, and so we're going to want to make sure that all of those points lie within that mod space. We don't really want to have redundancy, because if we're creating a polynomial in that mod space, and then we give, say q is 5, and we give a polynomial with an x coordinate of 1 and a polynomial with an x coordinate of, a pair with an x coordinate of 1 and then a pair with an x coordinate of 6. Because we're modding by 5, those are both going to map down to that x coordinate of 1, and because we are looking at a polynomial, that x coordinate is going to have that same value regardless of whether or not the original x coordinate is 1 or 6. So hopefully that makes sense. Okay, and then step 3, we of course need to construct our polynomial. Yeah, this is pretty much what I've been saying. So let's look at the example. So n is going to be equal to 4, k is going to be equal to 2. We're going to use 7 as our mod space. This is just what I like to call it. I don't know if that's like actually what it's called, but and we have obeyed the equation that we mentioned above. Okay, and our original message is going to have at x sub 1 we're going to have 3, x sub 2 we're going to have 1, and so on. And from Lagrange interpolation we can create this polynomial right here. And let's see, we are now going to create 2 additional points. We're going to evaluate our polynomial at 5 and at 6. And these are the values we're going to get. We get 6 when we evaluate at 5, and then we get 1 when we evaluate at 6. So that's what's going to be sent. We know that 2 of them are going to get lost. We don't know which 2, but we know that we're going to get enough points to create our polynomial. So yeah. Again, we're going to use the old method of Lagrange interpolation, where the top is the basically what we have to do is we have to create we have to sum up all of the delta i's times their corresponding yi's. And again, what a delta I looks like is, say our I is 1, we're going to want to have x minus every x coordinate that is not I, and then on the bottom we're going to want to have 1 minus every x coordinate that's not I. So hopefully that makes sense. Or yeah. I kind of used I and 1 there interchangeably just for this top example. And then this is where we multiply the y by the corresponding delta I, and then this is how we get that polynomial. Yep, and so notice how 1, 3, 4, and 5 were the only x values that we had. I feel like I've said it a couple times, but it should be fairly clear why, even though these are the only points that we have and these are not all of the original points, we still are able to create a polynomial that is the same polynomial that we created given our original points. Really quickly, what happens if n minus 1 packets are sent over? Well, if that's the case, then we don't... I think they meant n plus k minus 1, actually, or maybe I said that wrong. But if that's the case, then it kind of goes back to something that we mentioned last video, where now one of the points is kind of free floating and it can be any value in our mod space, right? If we are missing 2 points, then it can be any value in our mod space times any value in our mod space, so it becomes like exponentially worse. If that doesn't ring a bell, I would suggest watching my video on note 8. I think note 8, yeah. Okay. And now we're going to look at another version of interpolation, and I like this one a little better personally. And basically what it's going to rest on is the idea that we have as many constants, I guess, in front of these x terms, as we're going to have pairs that we need to use to construct a polynomial of degree d. So really quickly, what I mean by that, say we want to construct a polynomial of degree d, we're going to need d plus 1 pairs, right? If we know that our polynomial is of this form, a0 and has a 1 all the way up to ad, then that itself is d plus 1 a's. So basically, we can essentially just sub in what our x is at each. So basically, we're going to take this form, and we're going to sub in the x value, and then say that that is equal to the pair's y value. And we're going to do that for every equation, and we're essentially just going to set up a system of equations and solve for all of the a's. We're going to treat the a's as kind of what we are looking for. So I will walk through an example. Hopefully this will make more sense once it's drawn out. So let's switch over to Paint. Okay, so we know p of x is going to be of degree 2. So that means we know that p of x is going to be of the following form. So a2 times x to the 2 plus a1, sorry, that plus this, that is bothering me, a1x plus a0, right? I'll just get off to the side that our degree is equal to 2, and really quickly let's just see what our old points were. Negative 1, 2, 0, 1, and 2, 5. So negative 1, 2, 0, 1, and 2, 5. Okay, so I'm going to switch back over, and now we should have enough information to figure out what p of x looks like. So I'm basically just going to do what I said. I'm going to create 3 equations of this form where I'm going to plug in, say, the x value into all of the x's, and then set that equal to the corresponding y value. So let's just do that really quick. So we're going to say, and also, let's see, we have to keep in mind what mod space we're dealing with. So I think for now, because it's not explicitly defined, we're not going to worry about that actually. So let me make sure to switch back over. Okay, so yeah, just really quickly, a2 is going to be, or what is this? Yeah, so we're going to sub in this pair at first. So a2 times negative 1 squared, a2 times 1. So then we're going to say a1 is x is negative 1. So really quickly, I'm just going to make this. And then a0, that is just going to be a0, doesn't have an x tied to it. And then we're going to set that equal to 2. Okay, now we're going to look at our next pair. We're going to zero out all of these terms because our x value is 0, and then this is just going to be set to 1. So we're going to say a0 is equal to 1. That's pretty convenient. And again, repeat the process using the last pair. So we're going to say a of 2 times 4, yeah, and then we're going to say plus a of 1 times 2 plus a of 0, and this is going to be equal to 5. Okay, and you know, if it was a really long system of equations, we could use Gaussian elimination, but I feel like for most cases in this class, because you know it's not a linear algebra class, I'm pretty sure we're going to be given systems that are easy to solve by hand. So a0, let's see. We know that's equal to 1, so you know, how should we do this? Well, I'll put this up here. We're going to sub this equation into that right there. So I'm going to say a2 minus a1 is, or plus 1 is equal to 2. So a2 minus a1 is equal to 1. So we can say that a2 is equal to 1 plus a1. So hopefully that's still on screen. Yeah, just barely. And let's see. Maybe we can put everything in terms of, well, let's see, did I do that right? Honestly, systems of equations is sometimes shaky for me. Well, let's see, a1 is there, a0, we know, yeah, okay. So we're just going to take what we just boxed and we're going to kind of sub it in there. So we're going to say, what is this? We're going to say 4 plus 4 times a1, because we're just going to take this and then, you know, sub it into a2, and then we're distributing out this 4 right there, plus a1 times 2. Let's see. Yeah, we're going to put things in terms of a1, and then we know a0 is just equal to 1, so then we're going to set that equal to 5. So we'll say that 6a1, let's see, did I do that right? That looks a little funny to me. 1 second.
Is Lin J there?
Okay, yeah, so just continuing. So basically, looks like a1 is going to become 0. These 4 and this 1 are going to combine to get 5 equals 5. Subtract that out. We're going to get 6a1 is equal to 0. So a1 is equal to 0. This is going to be our, what is it? These are going to be our coefficients. So a1 is going to be equal to 0. a0 is going to be equal to 1. And then subbing in a2 is going to be equal to 1. So our final equation, I'll put it over here, is going to be x squared plus 1, I think. X squared plus 1. Yeah. Let me just double check. That sounds about right to me. Yep, okay. Just double checked with the notes. We are good. Okay, I'm going to switch back over to our notes. So let's see. Now we're going to move on to a different type of error. So before we were looking at erasure errors, now we're going to look at general errors. So here's the premise. We send n packets and we receive n packets, but k packets get corrupted. And again, we don't know which k packets get corrupted. So, you know, how are we going to combat this? We're going to send n packets plus 2k packets. So to just clarify, we don't know which k packets are corrupted, but we know that k packets are corrupted. Okay, and yeah, so let's go. I feel like the visual is a good thing to see. So n is equal to 3 in this example. We know that one of them is going to be corrupted, so k is going to be equal to 1. Because of that, we're going to send 2k additional packages. So our encoded message is going to contain 3 plus 2 times 1, which is going to have 5 messages in it. And the received message is therefore going to have these 5 messages. However, k of them are going to be corrupted where k is equal to 1. And then we are going to, we're going to be able to get the correct original message based on something that we're going to find out later. It has some funny name, I think. But anyways, yeah, this pretty much talks about what I did. So same approach as before. I'm going to construct a polynomial of degree 2 in this example. We're going to make sure that all of these, like 0.1, 3, 0.2, 0, etc., all of them will pass through our polynomial. And we got to make sure in this case that n plus 2k is strictly greater than, or sorry, strictly less than our mod space. Okay, and we're going to have k error terms, but we don't know which of them are errors, and so we're just going to imagine this set of error terms, which we won't know right off the bat. And we're going to use something called an error locator polynomial, which is just going to have this form. You know, x minus the first error spot's x all the way up to the kth error. So naturally that has degree k. And again, we don't know what these terms are. We just know that we can represent it as a polynomial in this form. And so we're going to use this equation right here that's pretty helpful. And basically what we're going to notice is that if we evaluate our original polynomial at index I, and then we evaluate the error polynomial at index I, then this will be equivalent to if we had evaluated the remainder at index I and multiplied that by the error locator polynomial. So to just examine why this is true, let's look at the visual again. So let's see. In our original error polynomial, we know that let me see, 3 0. So that's gonna be 2. Give me 1 second. Right. Okay. So sorry, it's confusing myself. So if we look at this example right here, and we put it in terms of this equation right here, we're going to see that our polynomial is going to be equal to some error term, where the error term is simply x minus e1, right? Because if we look here, the only term that is changed is going to be this one right here. Okay, and if we evaluate, let's see, if we evaluate p of x at any point between 1 and n plus 2k, we're going to get the same value that we get in the output, except for when we land on a value in which an error occurred. But if we land on that value, then we're simply going to get zeroed out by the e of x function, because in this case it's literally it would be x minus 2, and so when we plug in this 2, then we're just going to zero out this side, and then of course we're going to zero out this side because there's also an e of I. But anyways, let's look at the next part. So we're just going to represent the left hand side of this as q of x, and to think about what its degree is going to be, so p of x is of degree what is it, n minus 1, and then e of x is of degree k, so then q of x's degree is going to be of n plus k minus 1, and that should be form, not from. Yeah, so this is just going to be the form of these two polynomials, and we're basically just going to use the coefficient method of interpolation to come up with what the constants should be. Okay, and yeah, so what we have to do, let's see, is to notice that q of x, which again is literally just this, is equal to ri times e of I. Right, yeah. And we've got to make sure that we're modding by our mod space, and this will become clearer with an example. Let's see, n plus 2k unknowns. Yeah, so bk is always 1. Really quick, I believe that's just because that's just how it's defined. I mean, bk, b of 0, sorry, it shouldn't be bk. Or sorry, yeah, okay, so bk is always 1. That's because we remember that e of x is of this form, and so the highest degree is just going to be a bunch of x's times each other, if you think about that. So it's not going to have any coefficients. So that's why e of x has k coefficients, 0 through k minus 1, right? Yeah, okay. So let's go over an example because I think this would make it a lot clearer. So we're just going to reference that visual that we had above. So let me actually just put it down here so we can see it. Okay, so Alice is going to send the message to Bob. It's going to contain 3 characters. You know, they kind of mix in this thing about actual English characters. I think it's like cool but sort of unnecessary, so I'm actually just going to ignore it. So say we're sending a 3-character message. Our mod space is 7, so all of our characters range between 0 and 6. Okay, so what would the pairs be? We're going to have to use Lagrange interpolation to calculate p of x. If we use the method we used before, then we would come up with a polynomial of the form x squared plus x plus 1. And you know, I would encourage you to do this on your own, or just do it in discussion to get practice with it, but it's pretty straightforward. Anyways, we also know that k is equal to 1, so that means one of our messages is going to get corrupted. And just following our rule, that means that Alice is going to have to send 2k additional characters, and so she's going to have to send an encoded message of length 5. And so again, you know, we just had p of x evaluated at 1, 2, and 3. So if we need 2 more points, we're just going to evaluate it at 4 and 5. Okay, now we're just going to write out what the form of e of x and q of x will be. We don't know exactly what it will look like, but we know the degree of e of x and q of x. E of x is just going to be of degree k, where k is equal to 1, and q of x is just going to be equal to n plus k minus 1. Okay, so it's going to be equal to degree 3. And now we can create a system of equations, and we're going to follow this. I don't know why there's... Anyways, yeah, we're going to look at that to create our system of equations. So I think I can actually do this. Let me switch over to Paint. And I'm just going to rewrite, actually no, I'm just going to reference it. So let me make it new, don't save. Okay, so let's see, cubex. Let's see, so we have those points. We're just going to basically, like we said, set q of x. So I'm just going to write it out. So a3x squared, yeah. So a3x cubed plus a2. Wow. I have no idea how that just happened. Anyways, they're always listening, guys. Plus a1x plus a0, and this is going to be equal to ri times our error polynomial. So if we remember what ri is, just looking up here, given that we're evaluating at point 1, so yeah, so this one is just going to reference point 1, 2, and that means our ri value, or r1 value, is going to be 2, and then we're going to multiply it by our error polynomial, which is x minus b 0. Okay, and let's see. So if we just evaluate at x is equal to 1, then our mod space is 7 again, so you know, all of the x's will pretty much just go away, and we're going to be left with a minus 2b on this side, and in mod 7 that's just going to be a plus, yeah, that's going to be a positive b. So am I switched over to Paint? Yeah, it's going to be equal to a positive b, or a positive 5b. So we're going to say the following. So just remembering we're in mod 7, this is going to be equal to a 5b0. Okay, and this is essentially going to look like a3 x to the 3 plus, or sorry, it's going to be a3, plug in 1 to the 3, just becomes 1 mod 7. Same deal for that term, same deal for this term, a0. And then we're just going to subtract over this 5b0 minus 5b0, and that means it's just going to be equal to 0. And essentially we're just going to continue this for every equation, and I will show what that looks like. I'm just going to show the solution basically. Again, you basically just follow this form and input every point. You're imagining that you're on the receiving end, so you're inputting every point, you know, as you see it from there, and you're going to get this system of equations. Why there was a plus 5b? That I'm actually not too certain on. Plus 2. Let me think. Oh, okay. Right. Yeah. So, sorry, I should switch over to Paint. That was a silly mistake. So, yeah. So actually, let's see. Becomes 2 over there. Yeah, honestly, I'm not 100% sure why. Because, so we're inputting 1 minus b0. Oh, no, yeah, okay, jeez. Yes, so we input 1 into x, right? Then we get, and then this is what we get. We get 2 minus 2b0, and that's equal to, you know what's on the left side, right? So 2 is going to stay on the right side, but this minus 2b0, mod 7 is going to become 5b0. So, but see, we would still have to subtract it over to this side. So even though there would be a 2 here, I don't know, there might be something that I'm missing. 2 minus 2b0 mod 5. I mean, I don't know. I don't think I'm missing it. Anyways, hopefully your algebra is better than mine. So, yeah, basically we should get some sort of equation like this. We can obviously evaluate each term to, or perform Gaussian elimination on the system to find a solution for every term, and basically the answer is going to look like this. We're going to find out that our error polynomial is going to be let's see, x plus 6, which is congruent to x minus 1 mod 7. So that means that our error term, when we evaluate e of x at 0, that means that our error term is at spot 1, index 1, or I guess if we're following the indices of this, it would be index 1, right? So that means that our q of x is also x to the 3 plus 6, because the a2 and a1 terms get zeroed out. And that means that our error polynomial is, of course, x minus 1. And p of x is obtained by dividing q of x by e of x, just by nature of its setup right here. And yeah, from there we could just evaluate. So we know the error of the location, so now with the original p of x, we can evaluate at spot 1 to find out what the actual value should be. Okay, so hopefully that makes sense. And really quick, these are just some of the finer points. they have an explanation in the notes, but I'm sort of just going to drop them right here. So it's sort of known that the n plus 2k equations have solutions, and that they also, those equations, those n plus 2k equations are independent. And these kind of go hand in hand. So other than that, that has been, everything we're going to cover in Note 9. This has been about error correcting codes.